So our first unit of calculus is going to involve limits. So this is Unit 1, Lesson 1. And before we jump into limits, I want to take a little bit of time and revisit polynomial functions and characteristics of polynomial functions. So I've provided you with some examples of linear functions, both graphically and algebraically in the form of an equation. Quadratic functions, we all know, have the shape of a parabola. Cubic functions behave in such a way where the graph will begin one way and end another, so it like starts down and ends up. And then we have quartic functions, which are fourth degree functions. And then we'll kind of talk about higher degree functions in just a little bit. But what I want us to do is I want us to take a few minutes and really look at what each family of functions have in common. So I actually want to start with quadratic functions because these we're really familiar with, and then we'll go back and talk about linear functions afterwards. So here we have a function, f of x equals x squared minus 3. And hopefully you all remember that based on this equation, x squared means it's a parabola, or quadratic, which means it's a parabola, and that this particular function would open up. And specifically, this graph would have a y-intercept at -3. So I just wanted to kind of point out a couple of those key factors or key characteristics. Here we have another quadratic. This particular quadratic opens down and really should have arrows at the ends as well. And I'm hoping that you recall that the -3, the coefficient of x squared, indicates that this graph will open down. And then we have another quadratic, x squared plus 2x minus 1. And this is also a quadratic, should have arrows at the ends, but my calculator doesn't show arrows. So you've got two quadratics opening upward. You've got one quadratic opening downward. And we know that that happens based on the leading coefficient. The leading coefficient here is negative, so that means the graph will open down. And the leading coefficient for this example and this example are positive, so therefore the graph of these parabolas open up. So going back to the linear function, this would be your mom and daddy function. It goes through, the graph goes through the origin, and this line rises, and it rises because the coefficient of the leading coefficient is positive, and it's +1. This particular function is another linear function. The graph falls, and that's because the leading coefficient, or slope, is negative. And we have another, the f of x equals 3x minus 1, where we have another graph of a line that is rising. Okay, and that has to do with the fact that the slope is positive. All right, so now let's kind of drop down and let's talk about a cubic function. Again, all polynomials have domains that are infinite, or go from negative infinity to positive infinity. These three, or this cubic function, I have 3 examples. They are continuous functions. I like to say you can put your pencil on it, pencil or pen, and trace it without ever picking your pencil up. And that's true of all polynomial functions. But here's an example of a cubic function. This particular cubic function starts down and ends up. Here's another example of a cubic function. The graph starts down and ends up, meaning it points down. It starts by pointing down, it ends by pointing up. And this particular cubic function starts up and ends down. So these two graphs start and end the same way, and that's because their leading coefficients are positive. And then this particular graph has been reflected across the x-axis, and that's because the leading coefficient is negative. All right, then I have some examples of some fourth degree functions. Again, these also should have arrows at the ends of the graph. And you'll notice that this fourth degree function starts pointing up, ends pointing up. Here's another example, points up. And here we have a fourth degree function that's down, down. So what I'd like for you to do, if you haven't already, is I want you to kind of think about what do each family of functions have in common? A quadratic, no matter what the equation, will start and end the same way. So this is up, up. This one is down, down. This one is up, up. Look at a cubic function. A cubic function is down, up, down. A fourth degree is up, down, down. So what do you suppose would happen with a fifth degree function? So if you have a fifth degree function, the graph would more than likely behave where it starts down and ends up. So 1, 2, 3, 4, 5. So there would be an example of a fifth degree function. How about a sixth degree function? Well, a sixth degree function would start and end the same way. And what about a seventh degree function? So if you haven't figured this out, there are patterns to the graphs of polynomial functions. In this seventh degree, because it's odd, we'll start down and end up. Now let's go back to this linear function. So if you look at your fifth degree function and your third degree functions, your fifth degree and your third degrees all start down and end up. Sorry, that's a sixth degree. So your fifth degree will start down and end up. Cubic functions start down and end up. Well, what about your linear function? The degree of this linear function is 1. And if you look at this, the graph starts down and ends up. Points down, points up. So all odd degree functions, all odd polynomial functions, odd degree polynomial functions will start down and end up. So I'm going to raise this up. Odd degrees start down and ends up. All right, so that's odd. Those are odd degree functions. What do you notice about your even degree functions? Notice that your quadratics and your quartics, they start up and end up, start up and end up. Unless the leading coefficient is negative, then they're going to start down, end down. And if you look at this fourth degree function, the leading coefficient is negative, so it would start down and end down. So even degree functions will start up and end up. So this odd degrees are down, up, and even degrees, if I can scoot that up, are up, up. Okay, and that's very general, very non-mathematical ways of describing the behavior of polynomial functions. Now, there is a more mathematical way to describe the behavior, and that is by using notation to describe how the graph of a function behaves in the negative x direction and in the positive x direction. So I'm going to pull that aside, and I want to go to page 2 of our notes. Page 2 of our notes, we have a polynomial function. Well, we have 3 different polynomial functions. And knowing how the polynomial functions behave will help us in describing in words the left end behavior and the right end behavior for each of these polynomial functions. And then I want us to show using symbols, okay? So first I want us to do this. I want us to think about, what does this polynomial function look like in terms of how it starts. The degree is 5, so it's an odd degree function. The leading coefficient is negative. So when you think about odd degrees start down and end up. And when the coefficient is negative, the graph will start up and end down. Okay, so giving me just a simple idea of how this looks or should behave would start up and end down. And then it has, this one has 5 x-intercepts, 1, 2, 3, 4, 5. It changes directions 1, 2, 3, 4 times. So if this is what we have as an image of what this looks like, then how would we describe that mathematically? Well, we're going to describe this in terms of how the y values behave depending on how the x values behave. So here's what I'm going to do. Let's talk about in terms of as x approaches negative infinity. That little arrow means approaches or goes toward. Well, what that means is as your x's, as you move away from the origin in the negative x direction, you travel along the little graph here. Ultimately, what are the y values doing? The further you go away from the origin, excuse me, what are your y values doing? Well, because this is a 5th degree function, no matter how far to the left I go on this graph, no matter how far to the left I go, the y values or this graph continues to shoot upward, which means that as x approaches negative infinity, then y approaches positive infinity. Okay, now let's look at this graph moving away from the origin as x moves toward positive infinity. So if I'm looking at this graph and I'm traveling along the graph, now I'm going to ask myself, how far, as my x's move to the right, since this graph continues with the arrows, it indicates that the graph continues. The graph is continuing to move in the x direction toward positive infinity. The y values are getting bigger, but in the negative direction. So what we would say is the y values are going toward negative infinity. Okay? So when something is approaching negative infinity, that's just talking about a direction. So let's move on to this next example. Our next example, we have a quartic, a 4th degree function. 4th degree functions have that W shape, and since the coefficient is 2, positive, we know the graph will behave something like this. I mean, I'm not really sure about all of this, but I do know that the graph will start up and end up. So how do we describe that mathematically? So here, let's talk about our x values. So as x gets smaller and smaller and smaller, maybe I need to put this on an x and y axis. So as my x's get, as you travel along this graph in the negative x direction, your y values are approaching positive infinity. As you move away from the origin, your y values, as you move away from the origin in the positive x direction, your y values are approaching positive infinity as well. So as x approaches positive infinity, your y values approach positive infinity. So here, when we said that this graph on this example starts, typically a normal fifth degree function starts down and ends up. But this one is negative, so it starts up, and the y values pointing up go toward infinity. The y values going down approach negative infinity. So this piece of information right here corresponds to this information. And so this particular graph, we said started up and ends up. So what that means is your y values are going toward positive infinity at each end of the graph. Okay, now what about this next one? So our next example, we have a linear function. And what does that linear function look like? This linear function is going to fall. And so to describe the behavior of this function in terms of x's and y's, as x approaches negative infinity, as your x's move back toward negative infinity, the y values are approaching positive infinity. And as your x's are approaching positive infinity, as your graph moves away from the origin in the positive direction, your y values are approaching negative infinity. So here we know that the graph would start up and end down. And so y approaches positive infinity would be up, and y approaches negative infinity would be down. Okay. So let's create one more. How about that? Let's do, I'm going to create one more. Let's say we have a function f of x equals, I don't know, x to the third plus 1. So this is a cubic function with a leading coefficient of positive 1. So our graph is going to look something like this. Starts down and ends up. So for this graph, for this function, as your graph moves away from the origin in the negative x direction, these y values are approaching or going towards negative infinity. They just keep going down further and further. So as x approaches negative infinity, our y values also approach negative infinity. So as the graph goes out to the left, it also goes down. And then as x approaches, as your graph moves away from the origin in the positive x direction, your y values, as x approaches infinity, your y values approach positive infinity as well. So knowing how a function behaves and being able to describe it mathematically is the key to kind of understanding limits once we talk specifically about limits. So I want to stop there with this first part of this lesson, working with polynomial functions. The second part to this lesson, or the second video, will be where we focus on rational functions.